solution. It's a combination of pH and alkalinity, or there's always two factors involved. And the Earth system understands that. And when you perturb it with a buildup of CO2, it responds by bringing alkalinity into the ocean through weathering, and that then restores the alkalinity of the ocean despite prolonged high CO2 levels. The PTM is an intermediate case in our view of it, that happened over several millennia at a rate much slower than fossil fuel burning, and under those conditions, the deep ocean became undersaturated and dissolved calcium carbonate, but the surface ocean didn't become undersaturated, and calcification could continue. And so until very recently, and that's my last slide, until very recently, we had no indication of shallow water acidification for the PTM. And so my story until probably 6 months ago would have been that this was a prolonged event with deep ocean acidification because of the stirring in of the CO2 over long time scales, but that the surface ocean was able to remain buffered against that acidification. And that's very different from today, where we know that the CO2 buildup is more rapid and is causing acidification. Okay? So I think from one point of view, PTM is a really good demonstration of how carbon dioxide can drive climate change globally. It leads to the expected warming that we would anticipate based on climate models, and it leads to the acidification of the ocean. And in this case, it behaves just like our model expects it should, that the acidification would affect the deep ocean, but not the surface ocean nearly as much. The extent of surface ocean acidification really depends on the rate and duration of CO2 addition, and primarily the rate. And so we've taken those same models, and I cut the slides out to save time, but we've done the same model for various scenarios from the IPCC of fossil fuel burning, and all but the slowest rates of continued fossil fuel burning leads to substantial drops in the saturation state of the surface ocean, and then over longer time scales, the deep ocean acidification. Whereas when we run it over the slower durations of the PTM, we get the deep ocean acidification, but not in the surface. It also depends on the preconditioning of the ocean, how resilient the ocean was to ocean acidification. And I'm particularly fixated on this, not so much for the distinction between the PTM and the modern, because in both cases we had planktonic calcifying organisms depositing calcium carbonate on the seafloor, lining the deep sea and the tums of the ocean. That's what the limestone is. The carbonate oozes buffer against these acidification events. I also work in deeper time. For example, at the Permian mass extinction, we think that the Siberian traps were sending copious amounts of carbon dioxide into the atmosphere, and this was at a time when there weren't calcifying plankton. And so the expectation is that there was very little calcium carbonate on the deep sea floor. One wonders what you would even define the CCD as in a time when you didn't have planktonic carbonate production. But the saturation horizon was probably very shallow, and the ocean was unbuffered, and maybe perhaps that's why the Permian was the largest extinction event of all time, with a carbon addition that we've modeled to look a lot like the PTM. And so that's a story that's coming out more recently, but we think that the Permian and the PTM were similar rates and quantities of carbon addition. In the Permian, it caused a mass extinction, the biggest of all time. In the Permian, almost no biological consequences except for the poor benthic foraminifera. And only in the worst case scenarios for our simulations of the PTM do we get surface acidification that would significantly reduce saturation states for calcite or aragonite. And I didn't really go into it, but why this 10 petagram per year kind of modern fossil fuel burning threshold? I think it's related to the fact that the biological pump, the export of organic carbon from the surface ocean, is about 6 petagrams carbon per year. In other words, the biota's ability to take carbon dioxide from the atmosphere and shunt it into the deep ocean is operating today at about 6 petagrams per year. If you start adding CO2 to the atmosphere and stir it into the ocean at a rate faster than that, then the biological pump can't sequester that carbon into the deep sea. And so in the PTM, it was slow enough, the biological pump kept up, and the acidification was bottom up. In the modern, we've exceeded that capacity, at least to date, and so the acidification is progressing in the surface ocean and could lead to substantial acidification. And then the final comment here is that, like I said, up until about 6 months ago, that was the end of the story. And then we have been working with the USGS up in Reston to core the Maryland coastal plain, where there are very shallowly buried PETM sections. The group from Rutgers has been working for a long time on the New Jersey margin and have some further offshore sites. We're much closer to the paleo coastline, the fall line there along the coastal plain. We are finding, first of all, huge carbon isotope excursions, and this is where the plot thickens, significant dissolution, loss of carbonate organisms, in this case mostly nanoplankton, at the PTM in water depths of no deeper than 20 or 30 meters. And so all that I just told you, in a sense, could have to be reevaluated if we can demonstrate that the loss of the carbonates from these sediments, so they go from 20% carbonate to 0 in our shallowest cores in water, like I said, very close to the paleo shoreline. And so that either was the lysocline, the saturation horizon, coming way up onto the shelf and dissolving everything, which, by the way, is not so inconceivable. One of the things I always remember from Bob Garrels, he told me, because he stopped me, I said, Bob, I find that really hard to imagine that blah, blah, blah. Stop right there. He said, every time you think about saying it's hard to imagine harder. So we should imagine harder about how Pete Betzer could explain getting the CCD up to 20 meters in the ocean. It's incomprehensible from the point of view of modern oceanography. But I think we can do it with our models, and we're just about there with our PTM simulations, because when you think about how much seafloor there isn't a whole lot of seafloor between 2,500 meters and 500 meters. If you think about the hypsometric curve. So there's not a lot of carbonate to dissolve from the top of the mid-ocean ridges until you get up onto the slope, continental slopes. And so I think it's conceivable that the lysocline shoaled up onto the continental shelves. The other alternative, though, is that the CO2 was being added from above, like today. That, in our models anyway, would suggest that the rate of carbon, we've been grossly underestimating the rate of carbon addition for the PTM. I think the combination of the pH proxies with boron isotopes and better chronostratigraphy might ultimately be able to answer that question. Anyway, that's it. I'm happy to answer your questions. Thanks.
What about the action on the West Coast? I mean, you have this oyster industry that's in extremis.
Yeah.
In fact, isn't that related to basically the lysocline coming up on their narrow shell?
Yeah, that's right. So, we usually think about passive margin